Hi, in this section of the nuclear chemistry unit, we're going to be examining nuclear decay in more detail. We're going to be looking at the specifics of alpha, beta, and gamma radiation and what happens to the nuclei of atoms that undergo those forms of radiation. So, first of all, nuclear decay, what is it? Your author defines it as the spontaneous change in the nucleus of an atom. And when these changes occur, they result in the emission of radiation, and the radiation can take on numerous forms. We're going to look at mainly alpha and beta decay, and then briefly at some others. Another term for nuclear decay is radioactive decay, or simply radioactivity. So this slide shows that if you have a big unstable nucleus and it undergoes a decay event, what that means is it spits out a subatomic particle, in this case an alpha particle. And the nucleus then becomes a different element because of that subatomic particle being lost. During beta decay, an unstable nucleus will spit out a beta particle, and then there's a different sort of change, but it does become a different element, and we'll learn how to predict what element will occur in each case. But first we have to look at what exactly are the different types of radiation. So what exactly is an alpha particle? Well, alpha particles are referred to as helium nuclei because their atomic structure is exactly the same as a helium nuclei. If you strip away the electrons from a helium atom, what's left are 2 protons and 2 neutrons, or an alpha particle. The charge of alpha particles, being 2 protons and 2 neutrons, is 2 positive. They have a relatively low penetrating ability. They can be stopped by paper, usually thick paper, several sheets, or cardboard, or plastic. The change in the nucleus, this change here means the change in the nucleus. When an alpha particle is spat out, the mass will go down by 2, that's why the mass will go down by 4, that's why the minus 4, and then the atomic number will go down by 2, that's why minus 2. And it makes sense because it's losing an atomic number, 2 protons, and a mass of 2 plus 2 is 4. Okay, beta particles. Their identity is a high-speed electron. But it's an electron born not out of the electron cloud, but born out of the nucleus. And we'll get to how that happens in a minute. Their charge is 1 negative, just like any electron. Their penetrating ability is relatively moderate, can be stopped by specialized thick clothing. The change to the nucleus is rather interesting. There's no mass change, for all intents and purposes, and the atomic number goes up by 1. Now, this atomic number going up by 1 seems like you're adding a proton to the nucleus, but in actuality, it's a little bit different than that. A neutron is being changed into a proton. Now, subatomically, the difference between a proton and a neutron, other than the obvious charge difference, is that a proton is made of 2 up quarks and a down quark, and a neutron is made of 2 down quarks and an up quark, plus a beta particle, hence making it neutral. So when a beta particle is spat out, one of the down quarks switches to an up quark, and the beta particle is spat out. So the neutron changes into a proton, hence the atomic number goes up by 1. Okay, gamma radiation. Its identity is merely a high-energy electromagnetic wave. Electromagnetic waves are like light and X-rays, and gamma rays are the highest energy form of electromagnetic radiation that we know of. They have no charge. Their penetrating ability is extremely high, stopped only by the densest of matter. And they don't bring about a change in the nucleus, but usually are the result of other changes that have occurred. Okay, now this slide I show you don't have to memorize or know this radioactive decay chain, but it just shows you that generally speaking in nature, these events don't occur individually. They usually occur in the context of a larger decay chain until a stable element is reached. Excuse me. Okay, so you might have to predict or write a radioactive equation, a radiation equation, a nuclear decay equation. Talk about mincing words. Okay, so I might say radium is a radioactive element. I'll give you the isotope, radium-226, and I might say it undergoes alpha decay, and then say write the equation. the nuclear decay equation for this isotope. So what you would have to do is say, okay, alpha particle, what's an alpha particle again? Well, it's a helium nuclei. So then if I take this out of this, what do I get? Well, 88 minus 2 is 86. So then you look up element 86 and find that it's radon. And then 226 minus 4 is 222. Or conversely, 86 plus 2 is 88, and 222 plus 4 is 226. And then, of course, whenever part of a nucleus is broken apart, copious amounts of energy are yielded. Okay, so if I say that this isotope of iodine, iodine 131, undergoes beta decay, you have to think, okay, what is a beta particle? It's a high-speed electron. Okay. We say that the atomic number of a beta particle is -1. That doesn't mean that it has -1 protons. It just means that when you lose a -1, it's like adding a proton to the nucleus. So it's more for housekeeping purposes. So mathematically, 53 minus a -1, or 53 plus 1, is element 54, which is xenon. And then the atomic number doesn't change, so it's xenon 131. And then again, copious amounts of energy. Okay, gamma doesn't have its own version of a nuclear equation. It's pure energy, there's no resulting change to the nucleus, so there's no equation, and frequently, when energy is involved, it's in the form of gamma radiation. It could be heat, it could be light as well. Okay, another thing you might have to do is play nuclear detective. So I might have a nuclear equation and then say identify the missing item. So if we start with nitrogen and we bombard it with alpha particles, so we're trying to make this stable form of nitrogen unstable and change it into something else. So what would it become if this alpha particle stuck? Okay. Well, what's 7 plus 2? 9. What's element number 9? Fluorine. Okay. See how easy that is? This process is called alpha capture. Okay. I might also give you a radioactive isotope of fluorine and tell you that it changes into oxygen and gives off some unknown subatomic particle. What would that subatomic particle be? So you have to ask yourself, 8 plus what will give me 9? And 17 plus what will give me 18? And the answer in both cases is 1. And then you say, what subatomic particle has a atomic number of 1 and a mass of 1? And it would be hydrogen. In fact, this is how protons were first identified by, who remembers? Yeah, by our favorite, Ernest Rutherford. Okay, I might also give you beryllium and say that you're bombarding it with alpha particles. And then it changes into carbon. 4 plus 2 is 6. 9 plus 4 is, it's not 12. So there's some mystery subatomic particle that is being produced. And for a long time, they didn't know what this subatomic particle was. And it took a certain scientist to come along and identify that subatomic particle as being a neutron. Who remembers who that was? That's right, it was James Chadwick. Okay. Another possible equation, I might give you argon being bombarded with beta particles. And then ask you what might it transform into. So you would have to say 18 plus -1 is, and 37 plus 0 is, and then you can predict that we're transmutating argon into chlorine. This is called beta capture, okay, which is kind of the inverse of beta decay. Okay, I think we're going to stop there and leave the next section for the next video.